Okay, we will get started. So, we are looking at Bode diagrams, right? So, and we looked at the Bode plots of a few individual factors. The last factor that we are going to look at, or the last set of factors that we are going to look at, are is essentially second order factors, right? So, so we know that by and large we can write a second order transfer function in this manner, right? So, I am just considering the structure which we are already familiar with, okay. So, that is what I am doing. So, omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, right. So, that is a typical transfer function of a second order system that we have been considering in this course. So, now the question is that, like, how do I plot the Bode diagram of this particular factor, okay. So, let's start doing that today. So, this can be rewritten as 1 divided by I just divide by omega n squared in both numerator and denominator. So, essentially I will get it as s by omega n whole square plus 2 zeta by omega n s plus 1, right. So, that is what will happen, correct. So, if I divide both numerator and denominator by omega n squared. So, immediately what is going to happen is that, like, if I calculate g of j omega, so what would I get? I would get 1 divided by 1 minus omega by omega n whole square plus 2 zeta omega by omega n j, right. So, that is what I will have, okay. So, 2 zeta omega by omega n, right. So, that is what we will have as the sinusoidal transfer function. So, once I have this, what can I, how can I write the magnitude of this particular factor? So, I can say this is going to be 1 divided by square root of the real part square. So, the real part square is going to be 1 minus omega by omega n whole square, and this I have to square, that is the real part, then I take the square of the real part plus the imaginary part square. So, 2 zeta omega by omega n whole square, right. So, that is what I do, okay. So, then what will be the phase of this sinusoidal transfer function? That is going to be minus tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n whole square, right. So, that is what we get as the phase, right, of this particular factor, right, pretty straightforward algebra, okay. So, now let us look at the magnitude. Once again we will follow the same process as we did in the previous class with the first order factor. So, let us look at the magnitude of this factor, and then, like, let us try to figure out what are the asymptotes for this particular factor, right. So, we can immediately see that the magnitude of this particular factor in decibels is going to be minus 20 log to the base 10 square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n square, okay. So, that is what will happen, okay. So, this is going to be in decibels, right. So, what will happen as omega is very small? What do you think will happen to this magnitude when omega is very small when compared to omega n, let us say? So, the magnitude of g of j omega, you can immediately see that will tend to 0 decibels as omega is much smaller than omega n. Why am I taking omega n? Because we have omega divided by omega n, right. So, as a term, right. So, I have to compare the frequency in relation to omega n, right. So, when the frequency of interest becomes much less than omega n, which is the natural frequency of the system, we can see that omega by omega n becomes very small. So, obviously, omega by omega n whole squared also will be pretty small, right. So, in the square root term I will effectively end up with 1. So, I am essentially going to take log of 1. So, that I will get 0 decibels, right. So, that is what is going to happen when I have omega much lower than omega n. And what is going to happen when omega is much greater than omega n? Okay, so let me erase this and say when omega is much less than omega n. What do you think happens when omega is much greater than omega n? See, obviously omega by omega n is now going to be much greater than 1. Okay. So, now within this first term, if you look at it, you have 1 minus omega by omega n squared. So, that will effectively become minus omega by omega n squared, but you are squaring it. So, the first term is going to be like omega by omega n to the power 4, right. The second term is 2 zeta omega by omega n whole square. Now, which term is going to dominate? First term, right, omega by omega n to the power 4. So, now when you take the square root of omega by omega n to the power 4, what do we get? We get omega by omega n whole square, right. So, then if I take the logarithm of that, what will I get? I am going to get minus 40 log to the base 10 omega divided by omega n. Is it clear how, of course, this is in decibels, right. So, is it clear how we got minus 40 log omega by omega n? Because, I am sorry, what is it? Yeah. So, you can see that the first term tends to omega by omega n to the power 4, right. The second term is like omega by omega n whole square. Just think that omega by omega n is 10 power 3. So, the first term is going to be like 10 power 12, right. The second term is going to be like 10 power 6. So, the first term is obviously dominate, right. You take the square root, you are going to get omega by omega n squared. So, log of omega by omega n squared is 2 log omega by omega n. So, there is already a minus 20, you multiply it by 2, you get minus 40, right. So, that is why the magnitude tends to minus 40 log to the base 10 omega by omega n decibels when omega is much greater than omega n. So, obviously, we already know that this one is going to be the low frequency asymptote, right, okay, and this one is going to be the high frequency asymptote, just like what we did yesterday, right. So, this is going to be the high frequency asymptote, okay. So, that is what we will have here. Now, once again a set of questions that like the first one is, where do the two asymptotes intersect? Where do you think the two asymptotes intersect each other? Omega equals omega n. We can immediately figure out the answer as omega equals omega n. Why? Because you see that when you substitute omega equals omega n in the high frequency asymptote, you get 0 decibels, right. So, essentially 0 decibel line is the low frequency asymptote. So, essentially the two asymptotes intersected omega equals omega n, right. So, consequently omega equals omega n is the corner frequency, right, for this particular factor, right, the second order term, okay. The natural frequency is the corner frequency, okay. Is it clear? Because that is the frequency at which the two asymptotes intersect, right. So, the second question that we need to ask ourselves is that what is the slope of the high frequency asymptote? What do you think is the slope? So, the high frequency asymptote is minus 40 log to the base 10 omega by omega n, right. So, how do we figure out the slope? Let us say you go 1 decade farther, right, from omega, So, instead of omega you substitute 10 times omega, what do we get? So, immediately we see that minus 40 log to the base 10, 10 times omega by omega n, that is going to be equal to what? Of course, in decibels, that is going to be equal to minus 40 decibels, right, minus 40 log to the base 10 of omega by omega n in decibels, right. So, what is the slope? So, slope of the high frequency asymptote is going to be minus 40 decibels per decade, right. So, is equal to minus 40 decibels per decade. Okay, that is what we are going to have. So, please note that here the slope is going to be slope of the high frequency asymptote is minus 40 decibels per decade. So, as frequency increases, the magnitude decreases like minus 40 decibels per decade. Okay, that is important. Okay. Now, another question which we are going to ask ourselves is that when is the magnitude of g of j omega a maximum? Okay, or at what frequency? Okay. So, in other words, like at what frequency is the magnitude of g of j omega a maximum, right. So, that is a question we are going to ask ourselves. So, let us try to answer that. So, what is the magnitude of g of j omega? It is going to be 1 divided by square root of 1 minus omega squared by omega n squared whole square plus 2 zeta omega by omega n whole square, right. So, this is the magnitude, right. So, now when is this going to be a maximum? Of course, how can I find out at what frequency this is going to be a maximum? I differentiate, equate it to 0 and then like take the second derivative, figure out where it's the second derivative is negative for a maximum, right. But here I can use a simpler method. So, because since the numerator is 1, right, so I will have a maximum where the denominator is going to be a minimum. I can even remove the square root, right. So, at whatever frequency the term within the square root in the denominator is a minimum, that is the frequency at which the magnitude of g of j omega is going to be a maximum, right. So, let us say we call f of omega, some f of omega as 1 minus omega squared by omega n squared whole square plus 2 zeta omega by omega n whole square. Now, if we take the derivative, the first derivative of f of omega with respect to omega, what do we get? We get 2 times 1 minus omega squared by omega n squared times 2 omega divided by omega n squared, right. So, first I just then I have a minus sign, right. So, when I take the derivative of the term within the square, right, I will get a minus sign, right, because so let me put this minus sign here. Okay, then what will I have here? I will have essentially 2 times 2 zeta by omega n, correct. Then what will I have? I will have 2 zeta by omega n, correct. So, this should be equal to 0. Okay. So, now if I process this, what will I get for omega? Can you calculate and tell me? So, you can see that I immediately have this omega n squared cancelling off with this omega n. Let us say this 2 cancelling off with these 2s, alright. So, what will I have? I will have minus 1 by omega squared divided by omega n squared. Obviously, omega is not 0, right. So, of course, I can have 2 solutions, okay. We'll come to that shortly, like so plus 2 zeta times omega is equal to 0, right. So this has two solutions, right. I just simplified this and wrote it. So obviously, like omega is 0 is one particular solution, right, it can be 0, right, or the term within the square bracket is 0, that will imply that 2 zeta is going to be equal to 1 minus omega squared by omega n squared, okay. Sorry, this should be 2 zeta squared, right, correct. Yeah, I think I missed a zeta here, right. So 2 zeta square. So this will tell me that omega can also be omega n times square root of 1 minus 2 zeta square, okay, correct. I am just rearranging the terms and doing some simple algebra. Now, when will this solution be a real number, because we are dealing with frequencies, right. See, I want a positive real number, right. When will this solution exist? This exists only when 1 minus 2 zeta squared is greater than 0, or in other words zeta should be less than 1 over root 2, right, 0.707, right, 1 over root 2 is 0.707 approximately, right. So, sorry, yeah, but anyway zeta is a positive number, okay, of course, yeah, okay, when we started off I have to say that zeta and omega n are positive parameters, yeah, you are right in general, but since we are essentially dealing with systems where zeta and omega n are positive, so this is what I will have, right, okay. So this frequency omega r is called as the, have you encountered this frequency before? This is what is called as a resonant frequency. Okay, and of course it exists only when zeta is greater than 0 and less than 1 over root 2, okay, otherwise it doesn't, okay. For zeta greater than 1 over root 2, omega tending to 0 will give you the maximum value, that is the 0 decibel value, okay. But for zeta between 0 and 1 over root 2, like you have the resonant frequency, okay, basically giving you the maximum value of the amplitude or magnitude of the sinusoidal transfer function for this second order factor, okay. So what is this resonant frequency? See, we had we already defined a couple of frequencies, right. So what was natural frequency? See, you take a second order system, let us say you remove the damping, right, then you give a perturbation, the frequency at which the undamped system oscillates is what is called as the natural frequency, right. And also if you look at it, let me write it as an aside, if you look at an undamped second order system, so undamped second order system, the Planck transfer function is going to be like omega n squared divided by s squared plus omega n squared. Do you agree? So that's how we got the we have the visualization, right, of natural frequency. You give a perturbation, okay, or essentially then the frequency at which the output will oscillate is essentially the natural frequency. But if you also give an input which is essentially, let us say, sine or cosine of omega n, let us say you give sine omega n t, what is going to happen to the output? We are going to get omega n squared times omega n divided by s squared plus omega n squared whole square, right. So once I have this, what will happen? I think we already discussed these things, right. What would happen once I have s squared plus omega n squared whole square? I am going to have a t sin t or t cos t, right, term. So consequently, what will happen to the magnitude of y of t? It will go to infinity, right, as t tends to infinity, right. So this is another visualization of a natural frequency. That is, if you have an undamped second order system and you give an input which essentially which has a frequency equal to the natural frequency, the output will just explode, okay, to infinity, okay. That's natural frequency, okay. That was the first term. What was undamped natural frequency? Sorry, this is the natural frequency. What is damped natural frequency? Damped natural frequency was the frequency at which the damped second order system oscillated, right, when the damping ratio was between 0 and 1 in response to an step input, right. So we looked at omega d, if you remember, right. So there are 3 natural frequencies of interest. So the first one is natural frequency, which by definition corresponds to the undamped system, right. The second one was the damped natural frequency, which essentially corresponds to an underdamped second order system, okay, and the damped natural frequency was omega n times square root of 1 minus zeta square, right. So physically, what is the notion of this damped natural frequency? We have a stable second order system. You give a step input, the frequency at which the corresponding output would oscillate is what is called as the damped natural frequency. And even if you give a sinusoidal input equal to the damped natural frequency, the system output would be bounded because you have an underdamped stable second order system, okay, no doubt about it, okay. Yeah. Now the third frequency is the resonant frequency, omega r. So what is this omega r, which is essentially omega n times square root of 1 minus 2 zeta squared? This essentially means that I have a stable underdamped second order system with damping ratio between 0 and 1 over root 2. If I have such a system, this is the frequency at which the amplitude of the corresponding sinusoidal transfer function will be a maximum, okay. So that is the implication, okay. So or in other words, if you give a sinusoidal input equal to whose frequency is equal to omega r, you would get the maximum amplification of the input, because the amplitude of the transfer function is maximum of this frequency. That's what we have seen, right, isn't it? Okay. So that is the physical meaning of the resonant frequency. Resonant frequency, resonance and resonant frequency still correspond to a stable second order system, but then it is bad in practice because of the amplification of the oscillations. Because what is this physically, what is this magnitude of g of j omega? If you recall our derivation, the output, steady state output was u magnitude of the input times magnitude of g of j omega. So the output is also going to be a sinusoid, but the input amplitude is going to be multiplied by the magnitude of the sinusoidal transfer function. So imagine a frequency at which the magnitude of the sinusoidal transfer function is the maximum. So the output amplitude, which is a sine wave, that will also be a maximum there. It is still bounded mathematically, okay, but physically it may create issues, okay. The system is still stable, no doubt about it, right, but then resonance can lead to oscillations of reasonably high magnitude, which can cause structural damage, okay. So one famous example, like which is typically given to illustrate this is what is called as a Tacoma Narrows bridge collapse, right. So you please search online and watch the video. Tacoma, of course, Narrows bridge, okay. So you will see that the wind essentially excited the resonant frequency and the entire bridge swayed. Okay, yes, mathematically it's bounded, the amplitude is bounded. So, but what happened? The structure failed, okay, because of the excessive oscillations, right. So, that is what happened. So, just watch the video, right. So, that is resonant frequency, right. So, that is why I just wanted to do this analysis to convey the difference between natural frequency, damped natural frequency and resonant frequency. I hope the physical meaning is clear for each frequency, because this understanding is extremely critical when we want to analyze second order systems, right. So, and please note that resonant frequency once again is applicable only for those second order systems where the damping ratio is between 0 and 1 over root 2, okay. I hope this point is clear, right, okay. But we are not done with the derivation yet. As homework, what I want you to do is that you have to take the second derivative and then ensure that f of omega, f double prime omega is going to be positive at this frequency, right. That I leave it to as homework, because whenever you do maximization or minimization, you need to do both steps. I can't leave it hanging like this, but I am going to leave it to you as homework, okay. So, as homework, evaluate the second derivative, okay, and comment, okay. So, that's essentially homework. Obviously, you will see that at this resonant frequency, the second derivative is positive. So, as a result, the magnitude of g of j omega will be a maximum, okay. So, because magnitude of g of j omega is 1 by f omega, right. So, that is why when f omega is a minimum, magnitude of g of j omega will be a maximum, okay. So, that is what we will have, okay. So, please do that, and we can easily show that this is also I am going to leave it as homework. So, the magnitude of g of j omega, the maximum value, which is the magnitude of g of j omega at omega equals omega r, is going to be 1 divided by 2 zeta times 1 minus zeta square, okay. So, this you just need to plug in the value of omega in that expression, okay. You will easily get it, and the phase of g of j omega at omega equals omega r, you will if you substitute in that equation for the phase, you will get it as minus tan inverse square root of 1 minus 2 zeta square divided by zeta. Immediately you see that the maximum magnitude and the phase at the corresponding resonant frequency depend only on the damping ratio zeta, okay. So, that is what we have, okay. Please, you can just substitute and then very straightforward, you just substitute and then figure out.